Okay, welcome to part 2 of chapter 7, Stoichiometry. We're going to look at now balancing combustion equations. Combustion equation is one where compounds with formulas such as C, H, and O, where there could be an subscripts X, Y, and Z on any of those elements, should they be present. Such a compound is combined with O2 to always make the product CO2 and water. For combustion equations, the balancing process usually begins by trying to ensure that the correct number of carbons are balanced by focusing first on the number of CO2 units and the coefficient for such compound. Secondly, hydrogens are balanced from the compound by inspecting the number of water molecules found. And lastly, O2 is balanced. Fractions can be used for simplicity, and a multiplication can occur afterwards to eliminate such fractions. Okay, here's an example where a compound C5H8O3 is combusted with O2. Again, you see the only two products are CO2 and water. So the first step is to balance the number of CO2, so a 5 is needed here. We're now balanced in carbon. We jump back to the more complex formula here. Look at the hydrogen now, so there are 8. So a coefficient of 4 here would satisfy the requirement for hydrogens. We can now total all the oxygens and the products, and then try to bring a balance here in the number of O2s to do so. So you can see here we have 10 oxygens from the CO2, and we'll have another 4 from the water, so that's 14. We have 3 already in the compound, so that's 11. So 11 halves would provide the balance needed. At this point, we can multiply this equation by 2 all the way through to get the final answer. So times 2. And so we would have 2 C5 H8O3 plus now the whole number 11 O2 and 10 CO2 molecules produced. And finally, the 8 water molecules. Okay, very good. So here's another example. This is propane and the combustion of it. Take a moment to try to balance this equation. You may pause the video and I'll quickly go through the answer in a moment. Okay, so the process again begins by focusing on the most complex formula. We begin by looking at CO2 to balance carbon in the propane molecule, so 3 is needed out here. We turn back to the propane molecule and look now at the 8 hydrogens. And so placing a 4 out here will give us the 8 hydrogens needed. We can now do an oxygen tally. At right in the products, we see 6 oxygen molecules from CO2 plus another 4, so that makes up 10 for the oxygen in the products. Simply applying a 5 as a coefficient on the O2 molecule in this case completes the exercise. Okay, so for a more formal slide, here's the answers. Okay, moving on and now thinking about moles and what these coefficients mean for us in the chemical equation. We can start asking ourselves some questions. For example, if we were to start with 2 moles of propane and lots of oxygen, how many moles of CO2 can be produced? Take a minute to think about this. Provide an answer. Okay. Okay, so it's likely that you found that you needed 6 moles of CO2 that could be produced. How about this question? With the same 2 moles of propane and lots of oxygen, how many moles of water can be produced? Take a minute again, and you may pause the video if you need to think about this. Hopefully you settled on 8 in this time. So notice that for every 1 propane molecule, we were to get 4 water molecules in this case. So if we double that, 2 molecules of propane, we should get 4 molecules of water. Or similarly, 2 moles of propane, we should get 8 moles of water produced. Okay, here's another example that we'll use. Please take a moment to try to balance this equation. You may pause the video and resume as needed. Okay, so hopefully you found that you needed the following coefficients in the balanced equation. Let's ask a couple more questions to focus on the idea of stoichiometry. So for every 1 mole of ammonia reacted, how many moles of NO do you think are produced? Hopefully this one isn't too challenging. Notice that there's a balance in the coefficients of 4 and 4 for the 2 materials in question. So if there's 1 mole of ammonia reacted, we should produce 1 mole of NO. Answer C. How about this in turn? How many moles of O2 will react if 2 moles of ammonia are to react? So notice that we're focusing on the reactant sort of stoichiometry in this case. So if 2 moles of ammonia are to react, we need half of the coefficient out here. So half of the equation is to be used. So in other words, half of 5. So I might expect answer B here to be the correct one. Okay, and then one last question here to get us thinking more about stoichiometry. So which of the following must be the same before and after a chemical reaction? Again, take a moment to consider the options and come up with your answer. Okay, so hopefully with this question, you settled on A being one correct option. We have the law of conservation of mass that helps us with understanding that option A is correct. B, the number of molecules of all substances involved in chemical reactions. That does not necessarily need to be true. We can have some molecules that combine to give only a single product, or we can have some molecules that disintegrate or create new products of lighter mass. So we can create higher number of molecules through a reaction, or a lower number of molecules. So this isn't correct. The number of atoms in each type involved must be conserved. So this is again a different iteration of the law of conservation of mass. We are not allowed to destroy the type of atoms given the stability of the nucleus. So the correct answer here is going to be D. Okay, here's another question. How many rust molecules, Fe2O3, would be formed if 8 iron atoms were reacted with 12 O2 molecules? Again, you can take a moment to try to come up with your answer based on what you see in the equation. Pause the video as needed. Okay, so in this question, it's a little bit more tricky. We have information based on 2 reagents, and 2 different coefficients are provided. And notice that their balance is different than the balance reflected in the coefficients of the balanced equation. So you can see here that we consume more iron by unit number in the coefficient than the O2 molecules. So given that 8 iron atoms are needed, it would seem that we have too much O2 loaded in this hypothetical question. One way to work towards the answer is to create something called a mole ratio from the coefficients in the equation. Okay, so a mole ratio can help us understand the ratio of reagents in an equation. So we know that there are two Fe2O3 molecules in balance with 4 iron atoms in this equation. Okay, so let's see how we can use that mole ratio to help us. We know that 8 iron atoms were used in the reaction. We can multiply by that mole ratio, which told us that there were 2 Fe2O3 molecules in balance with 4 Fe atoms from the balanced equation. And so 8 times 2, 16 divided by 4. We should be producing 4 Fe2O3 molecules as we cancel the information using that mole ratio. Also notice that we've been told that 12 O2 molecules were used, and so we would expect that that is more than what we need given the coefficients in the balanced equation. We can also use that a different mole ratio to help us understand what is needed there. So if 8 iron atoms are to be used to help answer the question how many O2 molecules are needed, we'll use a different mole ratio based on the coefficients in the equation. So for 8 O2, for every 3 O2 molecules that are reacted, 4 Fe atoms can be consumed. And so this tells us that 8 times 3, 24, divided by 4 is going to be 6 O2 molecules are needed. And given that 12 were loaded up, we would expect 6 extra. Okay, so the first answer here is that 4 should be the correct answer for this question. And we've decided using the mole ratio that we can predict that there would be 6 oxygen molecules left over. We have here now the idea of something called the limiting reagent, what we run out of first. So limiting reagent or limiting reactant. You can see here that since we had excess O2, we used 6 of the 12. All of the 8 iron atoms were consumed in the reaction, and so this identifies iron as the limiting reactant. Okay, so with this, we've now got a new technique for handling stoichiometry and some quantified questions where we can transform information using the balanced equation. So in an example where we have 2 moles of C8H18 being combusted, we can predict how many moles of CO2 can be produced. And so based on 2 being the coefficient and 16 being the coefficient for the 2 materials in question, and the question asking about 2 moles, it's a simple answer to assume that we'll get 16 CO2 molecules produced. Similarly, we would expect 18 water molecules to be produced. For a more difficult question where we may need to consult or use a mole ratio, we can ask a question about 0.5 moles of C8H18 and try to determine how many O2 molecules are used. So again, 0.5 moles of this compound, putting the units here, C8H18 multiplied by a mole ratio. Trying to get into O2 units, so there are 25 O2 units needed for every 2 of the C8H18 units that are needed. And following this mathematics, we can get to the answer. So here you would find that 6.25 moles of O2 would be needed. And so this is how we use moles and ratios to relate substances and quantities using balanced chemical equations. Okay, so the takeaway message here is that mole ratios have been used here on the previous couple of slides and helped us answer these quantitative questions. Okay, so recall before we knew that we could go from a mass of a substance to moles by simply using its molar mass of the compound, something we can use from the periodic table and the formula. And so once we have a generic reaction with balanced coefficients in that equation, we now have the ability to create various mole ratios to allow us to transform moles of one particular moles information from for one particular species into another using that mole ratio. Of course, we knew from earlier work that we could go from mass to moles using that molar mass information. So now we have sort of a conceptual map here to go from mass information in A all the way through to mass information in another species in the equation. Okay, so here's a complex example which I'd like you to take some time to try. It involves a power plant that consumes a huge number of kilograms of natural gas. You can see that it's going to be a combustion type reaction where natural gas, methane, is going to produce CO2. And we know the other product would be water because of the combustion reaction. And so based on this, you should be able to answer a question like how many kilograms of CO2 should be produced from this equation, or from this amount of kilograms of natural gas combusted. Okay, so you would begin by listing and balancing the chemical equation. So here you have methane, natural gas, requiring 2 O2 molecules to produce CO2 and water in the combustion reaction. And we're going to use that and mole ratios to answer this question. So please pause the video here and see if you can answer this question, and we'll move on to show you how we do this using mole ratios. Okay, hopefully you've had a chance to try this. So the first strategy was to try to transform the kilograms of methane into moles. Okay, so that's sort of mass A into moles A from our previous generic equation slide. And so we begin by taking kilograms into grams. Okay, so that's the first step here. After having done so, we use the formula and the periodic table to decide on the molar mass for methane. Use that to go into moles, and we now know the moles of methane in question, corresponding to this sort of mass of methane. Okay, next we're going to use a mole ratio to switch from methane into CO2. So reagent into product to help us there. We saw from the balanced equation that there was 1 mole of CO2 for every 1 mole of methane in the balanced equation. So using that same number from before, we can now switch the identity of the methane into moles of CO2 by dimensional analysis type approach. So cancel moles of methane, cancel moles of methane. We inherit the units of moles CO2, and we now have this as our preliminary answer in moles. Trying to get back to an answer in the appropriate units, kilograms this time, we're going to need the molar mass of CO2. So that's reflected here as the 44.01 grams per mole value. So we can now transform moles CO2 into grams CO2. And then getting into kilograms, we'll need to cancel grams and end up in the kilograms shown here. Sorry, didn't mean to erase, didn't mean to do that. There we go. Okay, and so you can see that the final final answer here is going to be 6.0 times 10 to the 11 kilograms of CO2. Apologies for that. There was an error there. Let me correct that. Kilograms. Apologies. Okay, very good. That ends the lesson 1 here from chapter 7 on stoichiometry. Thank you for watching.